In mini lecture 21, let's spend a little bit of time talking about initial conditions. I want to bring a little bit of the differential equation content into this course and perhaps link it to a little bit of a practical context, if you will. How these things that you learn in your differential equation course have real practical connections and meaning in terms of circuits. Doesn't just exist in circuits. They exist in many other engineering topics, both in mechanical and civil. You have the same kind of idea. And today we're going to talk about initial conditions. Of course, we talk about initial condition in the context of a first order circuit. All right, so I'm going to go to the document camera. I'm going to do a little recap, why we are where we are, and then we move on from there. So let's see here. Let's share screen. Okay, so we are looking at circuits. Again, we're looking at first order circuits. And what we're talking about in first order circuit, one energy storage element in the circuit. So generally speaking, we're talking about either one inductor or one capacitor. All right. So that's what we are looking at right now. So these two, again, we look at the inductor, and then the capacitor, and we talked about what they are. They are passive elements, but what makes them different as compared to the resistor is that they don't dissipate any power. They have the ability to store energy at some particular time and release later. I've used the analogy of the gas tank. How much gas is in the tank is how much energy is in either your inductor or your capacitor. So again, let's put some voltage and current here. Let's put V1 here, I2. And then here, let's put V3, I4. Okay. And obviously, we need to know the relationship for these elements, these new elements here. For the inductor, is the voltage is proportional to the derivative of the current. Okay, that's really an important thing. And these things obviously are a function of time. And for the capacitor, it is the current as a function of time that's proportional to the derivative of the voltage. So these are really important relationship. This is what's going to bring the differential equation relationship into our nodal and mesh when we have these elements in there. Also important, we talk about power, instantaneous power, essentially voltage V1 of t times current times I2 of t. And if we put this, we're essentially looking at L di2 dt times I2. So we can write the power in terms of the current alone. And where I'm going with this, the current is really the important parameter for the inductor. And if we write also the energy stored at any time t, we know it's 1/2 L times the current squared on the inductor. So these are really important things for the inductor. Okay, and we can do the same thing for the capacitor. We can write the power for the capacitor as V3 of t times I4 of t, and that becomes V3 of t times C dV3 dt. And you can see for the capacitor, it is the voltage that's the most important parameter. And then finally, we can write the energy stored in a capacitor as 1/2 times C times V3 squared as a function of time. Okay, so these are the important formula for the capacitor and these for the inductor. All right, so when we put this, what we've been doing essentially, we've been looking at circuits that have DC sources, constant sources, okay, voltage or current types. Could be one, could be multiple, but the current and voltage type. And then the switches, essentially, these sources have been connected to the circuit, and via a switch, they get disconnected. Okay, so the next lecture, we're going to see the exact opposite. We're going to start with a circuit that doesn't have a source, and then the switch connects it to the source. So we're going to call this thing the step response for first order circuit. So, but thus far, we've been looking at circuits as a source, and then at some T naught, the source gets disconnected. So we're looking at what happened to the inductor or the capacitor in a circuit when that energy is being dissipated out into the circuit. All right. So the key thing that I say, if you think about your math, we're looking at, again, differential equation that looks like this, where both A and B are constants. Okay. So this is first order differential equation. That essentially what we get for first order circuits. And A and B are constant and are typically related to the circuit parameter. They're essentially related to the circuit resistors, sources, and what have you. And if you remember from your Math 45, I'm using X because X can be a voltage or current, so I'm using it as kind of generic here. So essentially from your Math 45, we know that X of t is equal to some constant C1 e to the minus AT plus B over A. Okay. So this is what your math course, the complementary response. And we're calling it the natural response. Okay. This is what your math called the complementary. We're going to call it the natural response. In essence, this response is the response for the homogeneous when B is equal to 0. And then this, your math call it the particular response. And we are going to call it in electrical engineering the force response. And the reason we call it the force response because it's essentially being forced by usually the source that caused this thing to be non-zero, assuming there's a source. Thus far, we haven't seen any case that this is non-zero, but this is coming. So we're looking at the two part of our differential equation response. The complement, what we used to call the complementary response, we're calling the natural response. What we used to call the particular response in our differential equation, we're going to call the force response. And of course, what's left essentially is finding C1 using some initial condition. So this is very much your differential equation course. So what I want to do is talk about what does that mean, that initial condition that we use. Okay, so in circuits, unless you had a very good differential equation instructor that essentially tried to bring the content into some practical applications, often, at least when I was in my Math 45, my differential equation course, we were given an initial condition and asked to solve for this differential equation. That's pretty much the way that I was taught way back when. But in reality, initial conditions come from some real physical meaning. The initial condition for circuits, it is the initial energy in either the inductor or the capacitor. Remember, we're dealing with first order circuits, so we're dealing with one. Okay, we either have one inductor or one capacitor. Okay, so the initial condition comes from the initial energy stored in either the inductor or the capacitor. Okay, so what does that mean practically from you? If you think, again, I'm referring to this particular equation right there. When I say the energy, I'm referring to these two things. Okay, that's the energy in the capacitor. That's the energy for the inductor. So what does that mean? We only use the inductor current or the capacitor voltage for initial condition. Okay. That's really a fundamental concept. Because again, if you think about the energy, so we're talking about the energy in the inductor is related to the current on the inductor. So if you think about our analogy of a gas tank, the initial condition is the initial gas that's in the tank after you fill it up. Let's say we go in and filling the gas tank. So we're having the energy essentially come up, and at some point you take off the nozzle from the pump, and again you start using your car. So the gas, so now we're looking at how much the gas tank is producing energy in for the car to run. That's the same concept for either the inductor or the capacitor. So the initial condition is the initial energy, the initial gas in the tank. So we use the current to the inductor because the energy on the inductor is proportional to the current square. And the reason we do that, because we know that energy in the inductor can never jump. Energy is a continuous. You can have a gas tank, you can go to zero, you can have no gas, but you cannot have essentially gas and then jump like this. So we know that the energy in the inductor is a continuous function. Okay, it's either rising or it's dropping, but it never jumps. So we know that, so we can use that for initial condition, because physically it is the initial, the energy is the initial condition. It's the initial energy that we're looking how essentially is going to propagate into the circuit. So regardless, so I'll make a statement here, regardless of what you are asked to calculate, in first order circuits, you must calculate the inductor current or the capacitor voltage. They are the initial condition. So that's really important to note. So it doesn't matter if I ask you a voltage across some resistors or a current through some resistor, you always need to calculate the inductor current or the capacitor voltage, because that's the only thing we can use for initial condition in our differential equation solution, because we are guaranteed that the inductor current is continuous, it doesn't jump. And we also guarantee that the capacitor voltage is also continuous, it doesn't jump. What do I mean by that? For the capacitor, for example, if you have a capacitor that's essentially connected to a DC source for a long time, essentially the capacitor gives you zero current. But the minute that you have a change, a switch in the circuit change, the capacitor start essentially giving you a current. So the current tend to jump on the capacitor, but the voltage never does, because the voltage is the energy. At least the voltage squared is the energy on the capacitor. So we use these parameters, the inductor current. They are the only initial condition that we can use for first order circuit, either the inductor current or the capacitor voltage. So when we see second order circuits, we'll obviously use both when we have both elements in to create a second order circuit. But for the time being, we either have one inductor or one capacitor, so we have to calculate the inductor current or the capacitor voltage, regardless of what I ask you. So that should be there. So this is actually also laying the groundwork for what's coming in the next mini lecture, in which case we're going to look at what happened when we have current sources that are just being connected to the circuit as opposed to disconnected from the circuit. In essence, this B here is going to be not zero, it's going to be a constant. Thus far, we've been seeing the homogeneous case, which is first order circuit that has some kind of DC sources, and then it gets disconnected. And we look at what happened to the stored energy in the capacitor or the inductor into the circuit. We've been using that, but now we're going to kind of look at the reverse problem. What happened when we have a circuit and then the source is just being connected on? So it's going to be a slightly different in the next mini lecture.